Right. Just be patient, guys. I'm trying to get the best view possible. Ne? Just bear with me. Yeah. Let's try this. Good afternoon, everyone. Those who are here. I see two people are watching. Let's duplicate this. Okay. I'm just going to check if the view is better for you guys. So still continuing from yesterday, but we're doing two topics today. We'll be doing grade 11. Yeah, not bad. We could do better, but let's not ruin what we have achieved so far. All right. And then, yeah. So we'll be doing probability specifically for grade 11, and then so that tomorrow we can do functions. We'll also do calculus just to remind of ourselves of different scenarios that we can get in calculus. So in grade 11 we are going to be implementing the independent and dependent events using the product rule. We'll also be revising the Venn diagram, and then we'll also be doing possibilities of T diagrams and few contingency tables so that we can be able to be prepared for probability in general. It's going to be very quick because it's a very simple topic. I just want you to remember what is needed at every time. All right, let's look at this problems of this nature as we saw in grade 11, where you have to implement, you have to use the T diagram every time. Let's see. We have a bag containing 6 red balls. So we have a very big bag that has 6 red balls. Put your bag. Alright, let me just put it somewhere where I will do not bother me. So we have 6 red balls. And then we have 8 green balls, and we have an unknown number of yellow balls. So we have three different sets of balls, and then the probability of randomly choosing a green ball from the bag will actually be 25%, because we're dealing with probability. So we know that in terms of probability, your probability in total must actually be 1. It can be 1, or in between, you can say probability is between 1 and 0. This is how you put it, where this is 100% and then this is 0%. So if it's 0%, it means that thing cannot happen at all. If it's 1%, it means that thing can happen indefinitely. So 100 possibility of happening. So if your probability is 50-50, it means that it has half the chances of happening, the same as half chances of not happening, like flipping a coin. But let's look at this one. We have 6 balls in a bag. Let's just say at random we had 6 balls. We had 6 red, and then we have 8 green, and then we have yellow. Yellow is X, you don't know yellow. And then they say at random, if someone would have to pick a ball, and the chance of picking a green ball is 25%. The probability is 25%. So if we were to find the probability of us getting a green ball, remember green balls, how many do we have? We have 8 green balls. And in total, how many balls do we have inside the bag? We have 6 plus 8 that we know, plus X yellow balls. So when we divide this, they need to give us 0.25, because 25% divided by 100 will give us a probability of 0.25. So we need to get 0.25. 8 divided by the number of balls. So let's just add this one together. We have 8 divided by, this will give us 14 plus X is equals to 0.25. We can also write it as 1 over 4, and then so that we can make our calculations very easy. Let's come this side. So this is over 1, so we can say that 8 and then 14 plus X is equal to 1 over 4. You can also verify if 0.25 is 1 over 4. So let's multiply by 8 multiplied by 4. You can also use a calculator. it will give us 32. Okay? 8 times 4. Let's make sure. 8 times 4 is 32. And then we have 40 plus x must give us 32. And then our x value will simply be, as transposing that side, will give us 32 minus 14. So our x value is actually 32 minus 14, just to make sure is 18. So as we have seen, we have already seen the total number of balls there is equals to 32, and they say we must show that there are 32 balls in a bag. This is how we thought about it. It is 1 mark, so we can also make sure that we are able to justify why our value is 32. So our total number is just 32 balls. We have 32 balls in that bag. So the reason why I did this is for you to be able to understand the concept, because we are still revising it. So I'm still also reminding you on how things work, especially in terms of probability. When we are back running, then we start giving answers only for 1 mark, because I don't want people to be falling behind, and so I also reminded you about this. So yes, we have 25% of getting those green balls. Then we can easily show that we are actually having 32 balls in a bag. And somebody can also say, but because the total number is at the bottom, I will just say green balls divided by the total number must give me 0.25, and then I have green balls already, which is just 8 over, and then total number, we don't know, total number in the bag is equals to 0.25, and then this will be the same as 0.25 multiplied by t must give me 8, then t will simply be 8 divided by 0.25, and then our t will just be simply 32. But what I wanted you to understand is where is that 32 coming from, because we really need going to need the value of x at the later stage. So I wanted us to actually be clear on how do we go about getting that 32. So yes, they say show that there are 32 balls, so you can say green divided by the total number, because already we have 8 green balls that is given to us, even though we don't know the total number, because we just tried to prove the total number is 32. Hope that makes sense. Don't be surprised when I disappear from the video. I just also want to verify if we are still live and if the picture is still clear for all of you. So every other problem, I'll come and check if the video is fine. Awesome stuff. Right, let's move on. And then let's move on to 8.2. Same problem, same scenario, but this time we want to find out if a ball now has been we still have 6 red balls, still have 8 green balls, and we don't know the number of yellow balls, but from what we have done previously, we have the value of those yellow balls, because that was actually 32 minus 14, which gave us 32 minus 14. Last time I checked, it was 18. So can we confidently say these yellow balls are 18? So the total number of balls, they are 32. And we've discovered that from the previous problem. So what is happening is that a ball is drawn from the back and the color has been recorded and it's not returned to the back. So out of all those 32 balls, we have those 32 balls inside the bag, and then somebody picks out one ball, and after he has picked out, that's the first thing that they do, the first scenario, they pick out one ball. After they've taken that ball, they don't return the ball back. So it means that you will now have a total number of 31 balls because that ball was not returned back. So we have now 31 balls. Thereafter, another ball is drawn. Then he's going to withdraw another ball. And then from the back, and the color is recorded, it is also not returned. So it means now we're going to have now 30 balls because we have withdrawn a second ball. So I want us to see how we represent this in a Venn diagram. So we have, remember we have three sets of different colors. We have red, so we also have green, and then we have yellow. So I'm gonna try to squeeze in my T diagram this side so that people can see it. So I'm gonna have three branches because I have three different things. So I'm going to have the first one as red, and then the second one will be green, yes, and then my yellow. Good. Now the probability of me getting a red ball is the total number of balls at first. In the first scenario, when I was drawing the first ball, is that I had how many red balls? I had 6 red balls. And out of how many balls in total? I had 32 balls in this. So that is the probability of me getting a red ball. And then the probability of me getting a green ball when we are here will simply be how many green balls is actually 8 over 32, that's 25%. And then what is the probability of me getting a yellow ball? We said the yellow balls are just 18, so it's going to be 18 out of 32. So it's very important that we find the value of x, which is the yellow balls. So if you add this all in all, they will give you 32. Yeah? So this is the first scenario when we start putting the first ball. So these are the ratios, these are the probabilities. Now the second branch must have the same branch as the first one, because yes, you still have the red, you still have the green ball, and then you still have the yellow ball. Red, green, yellow. Red, green, yellow. I hope that makes sense. And then let me just also find a bit of space so that people can actually see it. Let me erase this. But it will make sense to you, yeah? It will make sense to you. Let me erase this. I want it to be a bit bigger. I'll erase this. Okay. The 3 first branches. 1, 2, 3. Red. This was green. And then yellow. We said this was 6 over 32. and then this was 8 over 32, and this will be 18 over 32. And then we have red, green, yellow again, red, green, yellow. Now we are here because we have pulled out one ball. One ball is gone and it does not return. If this ball was returned, it means these probabilities will follow everywhere because the ball is still there. But because it has pulled, the probability will change. Now, when you look at the probability, because it's coming from the red branch, you are going to interpret it in a way to say, if a red ball was taken out, now how many red balls will I have in this bucket? Because there were 6. But if the red ball was taken out, because we are in the branch where the red ball has been taken out, if the red ball was taken out, you will no more have 6 red balls, you will now have 5. And how many balls are there in the in that sack or in that container? There will now be 31 because we have removed the ball. So we are here. That's the second branch. And then you continue again. What is the probability of the green balls? If you remove the red ball, it means the green balls are still the same value. So we still have 8 of them, but now the total number is now 31 because the red ball has been removed. And then for the yellow balls, we'll still have 18 yellow balls out of 31. So that will be your probability for the second branch. And then when you go to the next branch, you forgot what you just talked about here. You deal with the green ball independently. If I took out the green ball, you focus on this branch only. Don't confuse this branch and this branch. You say, I took out the red ball, now I'm taking out another green ball. No, treat this one independently. So if I were to take out a green ball, it means the red balls will still be 6, but the total number will be 31. And then the green balls will no more be 8, they will just be 7 out of 31. And then the yellow balls, because I didn't take out any yellow balls, will still be 18 out of 31. So in each branch, what's going to be affected is what was taken out. So for this branch, we pretend as if the red ball was taken out. The possibility of a red ball being taken out, this was going to happen here. But if the possibility, the other possibilities is that if now the green ball has been taken out, we forget about what we just made as a possible outcome. We focus if now the green ball has been removed, and we go for the yellow one, as if it's the first time we take out the yellow one. So it's another possible outcome if the yellow ball was removed. The red ball will still remain as 6, and the total number is 21, and then the green ball will remain the same as 8 over 21. And then the yellow balls, they will be affected as 17 because you have taken out 1. So this becomes your probability for the second branch. Good. So it means that if we were to be asked, this branch will give us getting 2 red balls. This one will be us getting a red ball and a green ball moving along the branch. Red and green. Red and yellow. And then for this branch, it will be green and red. For this one will be green and green, and for this one will be green and yellow. That's what coming from this branch. This one is coming from that branch. You move along the branch. And then this one will be yellow and red. This will be yellow and green. This will be yellow and yellow. These are coming from that branch. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9 possible outcomes that you might get from just withdrawing two balls one after the other. Even if you have to withdraw them at the same time and looking at them at the same time, you will still get the same possibilities. So this is how we draw our T diagram based on the scenarios. And then I hope that makes sense to everyone. And the other thing is, I can also give us a different example. Let me save this. If let's discard this problem. If I were to say maybe we have let me say instead of now 3, I had 2. I have 2 branches. I have a red ball. Okay. And let's make it a scenario. Let me just take this only. I want to make a scenario where we're going to return the balls back. So I have 6 red balls. And then I have 8 green balls. So firstly, I'm going to withdraw the ball and then put it back. Withdraw the ball and put it back. So my first withdrawal, from the back I have red and then I have green. But how many balls do I have in total? There will be 14. Total number of balls will be 14 and 6 of them are red. That's my probability of getting a red ball. And the probability of me getting a green ball will just be over 60. This is 60, 40. 14. Now, if I were to withdraw again, remember I still have a red ball and a green ball in the back. The total number of balls didn't change because I put the ball back. I still have the 6 balls of. I still have 6 balls, 6 red balls. I still have 8 green balls. So the probability will remain the same all the time. Because even though I have selected the green ball, I will select it and put it back. So the back remains the way it was. The composition of the back is still the same. So the probability will continue. If I withdraw again, I'm going to open the branches, so on and so on and so on and so forth, depending on how many times I take out the balls. I hope it makes sense. Right? So us putting the ball back or not putting the ball back in the bucket is very, very important. It's critical information. It will affect the probability. Let me just go and recheck. All right. Now the last question from what it says, calculate the probability that two balls drawn from the bag will have the same color. Né? Let me do this. Let's draw the T diagram again. Look, now we have space. That's our T diagram. 3 branches: red, green, yellow. Red, green, yellow. Red, green, yellow. Red, green, yellow. We said this was 6/32. Last time I remember. This was 8/32, and this was 18/32. This changed into become 5/31. This became 8/31, and then this became 8. Yellow was 18/31, and then green was actually, if you take out a green ball, we still have 6/31, and then green will be 7/31, and then yellow will still be 18/31, and then this side will be 6/31, and then green will be 8/31, and then yellow will now be 17/31. This way they are our probability. So the examiner is asking, calculate the probability that two balls drawn from the bag will have the same color. So we have red and red here, same color. We have red and green here from this branch, so the same color. Red and yellow. This will be green and red. This will be green and green. This will be green and yellow. This will be yellow and red. This will be yellow and green. This will be yellow and yellow. So we look for the one that have the same color. So these are the ones that have the same color. This branch, same color. And then from this branch we have green and green. That branch. And then this branch we have yellow and yellow. So I'm going to also highlight them with blue, the one that have the same color. So same color, moving along the branch from red and then going to red, same color. Let me see, that's red. Let me see if I can give another one so you can see from green, moving along the branch, going to green, same color, because we're having green and green. And then let me use green just for people to see what I mean when I say we are going to travel across the branch. And yellow and yellow. So our probability for us to have same color of those balls will simply be the probability of red and red plus the probability of green and green plus the probability of yellow and yellow, which will simply be the probability of red and red. Because you are moving along the branch, you're going to multiply. As long as you are moving on the branch, you are going to multiply. So for this one, it will simply be your 6/32 multiplied by 5/31 along the branch. So it's this probability multiplied by this probability. That's where I'm passing. And then plus, so this will be 8/32 multiplied by 7 over 31. That's hence your probabilities on the branches must be very accurate for you to get the accurate answer. And then plus the last one along this branch will be 18 over 32 multiplied by 17 over 31. So as you move along the branch, you multiply. When you move across the branches, you add. When you move, you multiply. That's why we have actually added all of them. And then you press this in a calculator and you find the probability. So our final answer will be, let me just press the calculator with you guys. I know if you're here, you'll be the one pressing the calculator. No? Plus, I hope everybody has their own calculator at home. I hope so. Alright. And then the last one, 18 over 32. And multiply by 17 over 21. And then the probability is 49 over 124. And somebody can say, which is approximately 0.395. Let me write a proper 5. So in terms of percentage, I'll multiply this by 100 will actually be 89.5%. So you have 39.5% chances of getting both balls to have the same time. Hope it makes sense. And yeah, practice. There are 2 problems. I've also have a series of questions, so if we can just stay on this video, you'll actually be fine. You'll be exposed to more of these problems as we move on with different scenarios. But what is important is your understanding to say, are you able to make sense of what just happened with these balls? Good. Let us now move. If you have any question, you can timestamp the video or just screen grab. What I'm going to do today is that all these pictures that I'm saving from the solutions, I'm gonna send them to you. Yeah, yesterday's ones and yesterday's one for both lessons have already been saved. They are on my laptop now. I'm just going to send them to you guys, and you will see which one we actually need. I was just scared to overwhelm you yesterday because people were very emotional. All right, let me just go and verify. Good, very clear, still good to go. Yeah, we have, this is a contingency table. So before we start solving problems, I want us to just to make sure we understand what this table actually represents. And when you look at, it's a combination of snacks. We have snacks, and then this is gender. So how do we interpret this? We say male who choose to eat vegetarian snacks. There are 12 out of a total of 150. When you tally these numbers, as you go down, this plus this will give me that. this plus this will give me that, and then this plus this will give me that, but also this plus this must give me that, this plus this must give me that, and this plus that must give me that. So on the sides and at the bottom are totals, so you can just add them. So sometimes you will have a missing number, so you know that this is total, you can just take the total, subtract by one of the number that is given to you, you get the middle number. If this is missing, you add this 2, you get this one. That's what the contingency table actually help us to do. And then you will see it's comparing a lot of things. This time is just comparing vegetarian, which is a type of snack, and gender. You can see that this is male or female. So now let us read the statement. It says, on a flight, a passenger could choose between a vegetarian snack and a chicken snack. The snacks selected by the passengers were recorded, and the results are shown in the table below. So the question is, first, was the choice of the snack on this flight independent? That's the word, independent. Then you have to remember now, once you see the word independent in probability, you need to know that it means that the probability of A and B happening at the same time will be equal to the probability of A multiplied by the probability of B. We call this the product. This comes immediately when you see this word. Independent or dependent. If the situation is independent, if probability of A and B happening at the same time is the same as to take the probability of A multiplied by the probability of B, and they are equal, then you can say that the two events are independent. If not, they will not be independent. So please guard against that. So it means we need to go and find the probability of a snack. Maybe we can pick any of the snack. Let's say we pick vegetarian, and then go and pick any gender. Maybe we say we pick the probability of a male, because we are comparing a snack or a male. So it means we need to test if this will be equal to the probability of as a vegetarian and a male. If they are equal, then we can say the two events are independent of each other. Somebody can also say, because I'm testing gender, I can pick any gender, I can pick any snack. So somebody can say, I'm going to pick chicken, the probability of chicken, and then check also if I multiply to the probability of a female. And then I must compare it with the probability I'm going to get for a chicken and the female. If they are equal, these two, then I can say the two events are independent. Are we okay? So let me just erase the side so that I can make some space. Alright, I'm going to now compare the two. I'm going to pick the probability of a vegetarian. Picking a vegetarian snack. Yeah? The probability of me of a vegetarian snack will actually be, let's look at the vegetarian. The total number of vegetarian is actually 32. You see that? So the probability of a snack being vegetarian will actually be 32. Total number is 150. and then the probability, let's take for example, because I'm a male, I'll pick a male, yeah? Of being a male, or finding the probability of a male, in terms of this will represent the snack, this will represent the gender. You can choose to pick the probability of chicken and take the probability of a female, or chicken and male, or vegetarian and female. I hope you get it. And then for a male, the total number of males is actually 67. So the probability of picking a male is actually 67 over 150. And then the probability of vegetarian snack, and that means is them happening at the same time, and being a male will actually be, we go to vegetarian, yes, vegetarian, and a male is actually 12. So this will be 12 out of the total number, which is 150. So let us see if you take this probability. I think 12 divided by 150, 0.08. Let's see when we multiply this, will it give us 0.08? 32 over 150 multiplied by 67 over 150. And our answer will be 32 multiplied by 67 divided by 150 divided by 150. Our answer is approximately 0.095. Pretty close, but yeah, significance different. But yeah, they're pretty close. So we can say these are not independent. If they ask you by show of calculation, you can also say PV and M, it is not equal to the probability of V multiplied by the probability of being a male. So as soon as you get the word independent, show that something is independent, or you strictly go to the product rule and remember that the probability of A and the probability of A and B happening at the same time is the same as the probability of A multiplied by the probability of B. That's what we actually have learned in grade 11. This has to deal with independence. Hope it makes sense to you. Good. Still good. Let's move. We now have independency that we find. Good. And then we're going to have new words here, or the words that we did in grade 11. Let's look at the question from one of the previous question papers. It says for any two events, A and B, it is given that P, A, and B is equals to 0. And then our is equals to 0, 1, 2. And then P, A, or B is equals to 0, 83. And PB is equals to 4PA. Then we have a formula. Remember, we have a formula that has to do with if our PA and B is equals to 0, we say event A are mutually exclusive. What does mutually exclusive means? It means that those two events cannot happen at the same time. Yeah? I don't know which example to use because in most instances I end up offending people when I use people to say there's two events where you say they are mutually exclusive. You cannot be a boy and a girl at the same time. But things have changed, so I've stopped using that example. Ne? Okay, so here are two events. It cannot be night and day at the same time. So the two events are mutually exclusive. They cannot happen at the same time. That's why this is the intersection, like when you have two events happening at the same time. Yeah? We have a value here. So these events, if this is A and this is B, these two events are not mutually exclusive because they can happen at the same time. There's an intersection there. But if you were to have an event of the sort and then there is no intersection between those two events, we say those events are mutually exclusive. They cannot happen at the same time because the probability of A and B is equals to 0. So if you want to test if something is mutually exclusive, we need to go and find out if P, A, and B is equal to 0. If it is equal to 0, then we will know that those two events are mutually exclusive. And then you also have another formula where we say the probability of event A or B happening will be the same as the probability of finding A plus the probability of finding B and then subtracting the probability of A and B. This is also one of the most important for finding the probability of A or B. And then if these events are mutually exclusive, it means this part will actually be 0. So for all mutually exclusive events, this formula will just be PA or B is equals to PA plus PB because these events are mutually exclusive. But yes, do remember, this is your other important formula. This is also very important for you to remember. How would you know that something is mutually exclusive? Is the probability of PA, A and B, or the probability of those two events happening at the same time, is it equal to 0? If it does, then we know that those are mutually exclusive. Now in this scenario that we have, already we have two events, A and B. It is given that P, A and B is 0,12. So already we know from this part, from this given part, we know that the probability of P, A and B is 0,12. It's not 0. Do we see that? So if they ask you, are the events A and B mutually exclusive? You will say, no, they are not mutually exclusive. If they ask you why, you can say P, A, and B is not equals to 0. Or you can write P, A, and B is equals to 0,12, which is not equals to 0. Just to show that you understand what actually justifies your answer to say these two events are not mutually exclusive. It's because the probability of A and B happening at the same time is not equals to 0. Good. And then if they say now calculate the probability of B happening, of event B happening, from the formula that we have, we're going to substitute using that formula. Let me use blue in terms of values. We have the probability of A or B happening. Let's see, we have A or B, yes, and we are given the probability of A or B happening was actually 0,8. The probability of A happening, do we have it? It was not given to us. So let's write it as it is. And then the probability of B happening will actually be, it was given as 4PA. So we're going to substitute 4PA. And then minus the probability of A and B happening was given as 0,12. And then we are simplifying because we are looking for the probability of B happening. So what we can do, substitute this to the other side, we add them together, it's going to give us 0,95. I don't know what's wrong with my 5s. I have twisted 5s. So 0,95, and then which is equals to, and I add these two to be 5, probability of A happening. Okay? And then it means that I have to divide this by 5. (0,95) divided by 5, so we get 0,90. Sorry, that's the probability of event A. So for event B, we're going to multiply that by 4. So we're going to have 4 multiplied by 0,19. And then we multiply this by 4, and this will give us 0,76. Good. So you need to, every time, these are the most important figures. And then what's the other one? Don't forget when you use that one. Only use this when you're trying to prove, or you are given that two events are independent. Good. And then we'll answer this one. Let me just check if we have to find. We're still okay, né? Good. All right. You will revisit the video, go back if you want to go back, and then if you have any questions, please feel free to ask me. And then what it calculates P not A. Normally, they can also write this. Ne? So what we can do, this will be the same as 1 minus the probability of A happening. So because already we have the probability of A happening. P not A will simply be 1 minus PA, which is 1. And then you see, even if you know the answer, I press the calculator just to make sure. So this will be for 9.2.3. So this will be our solution for 9.2.3. Straightforward questions. And I think it's about 10 marks.